Hey guys, how's it going? Aaron Brown here, and today we're doing our first live walkthrough of Term 2, Project 1, the Extended Kalman Filter project. So I'm a content developer with the Self-Driving Car Nanodegree program, and then so lately I've been doing a lot of updates with the EKF, UKF, and localization projects that utilize the simulator interface that gives it a nice kind of graphic component so you can see what the data is doing. So appropriately enough, today we're going to be walking through the latest version of EKF, which uses the simulator. So I don't want to give away too much of the project, but I guess fortunately enough, a lot of the code that you need in order to do the project is already in the classroom. So constantly throughout this walkthrough, I'm going to be referencing the classroom and the different sections of where you can find the code. But I'm also going to try to cover that the code detail as much as I can, just to give you a better understanding of what everything's doing. And then for the majority of this walkthrough, about 40 minutes. I don't know if it'll take the full 40 minutes since this is the first project. It kind of goes a little bit quicker than that. I'll just be screen sharing and showing you the code, and then also walking back and forth between the code and where I'm getting in the classroom. And then after that, we'll open it up for about 15 to 20 minutes for doing a Q&A where I can answer any questions. So that's basically the layout for this walkthrough. Let's go ahead and get started. So I'm going to go ahead and share my screen. The first thing I want to do is go ahead and clone over the project, and I can find that over here on GitHub for the Car N D Extended Kalman Filter project. So I'll go ahead and I'll grab a link for that. And I'll just go inside of it. And we'll kind of take a look at some of the files that we have. So for starters, for the simulator version, a big kind of update is that it uses WebSocket IO interface. And it's pretty similar to what we're doing back in term 1 when we had the behavior cloning project, except that was all in Python, and it was much easier to get the WebSocket server plugin code to work. Whereas here we're doing it in C++. There's a couple of different ways to install it. The caveats kind of come from that you can't get the latest version of WebSocket.io from GitHub, and you have to get a very specific version. I'll kind of walk through the steps I took in order to do it. I'm using right here Windows Ubuntu Bash, which comes free with Windows 10. And I have the latest version of that as well. I have the 16.04. And that makes it so it's pretty easy for me to grab WebSocket.io. All I need to do is check out this install ubuntu.sh script here, which will pretty effortlessly do the sudo apt-get install libuv1dev and the SSL dev environments, and then go ahead and check out WebSocket.io from GitHub, but only this version here, which is the version that works with the simulator, not the latest version, and then it'll just build it and install it. So if you have 16.04, you can just use that script. With Mac, I haven't tested it with Mac because I don't have it, but for the most part, that script seems to work as well. We're also looking at some other solutions too. You can use Docker for one, and there's students on Slack who have shared their own Docker images, and if you have the right Docker image with all the project dependencies, all you have to do is load up that image, and then you're good to go with all the projects right there. We're working on our own kind of Docker image too. Another thing that we're kind of exploring is maybe giving out CLion, a license for CLion, and then we'd have more control over setting up some of the dependencies ourselves too, so which would make it much easier. But currently, this is the latest way just to kind of go about and get WebSocket.io. So I'm gonna go ahead and close out of that script. I can also see the mac.sh1 over here too. And then if you're using the Mac, there's a cmake patch.txt that for majority of the Mac users seems to help with the installation. Other than that, we just have the project code itself, and we have our SRC, which has all the programming files that we need. The ones that we'll be working with today, so Eigen library is going to help us do all our matrix math. We're going to be working with Fusion ekf.cpp. That's where we're going to be kind of implementing the high level of the ekf. Then we have its header file, and it ends up that we might just need to initialize or declare some variables in here as well. JSON.hpp, don't worry too much about that. That's for the simulator uWebsocket.io interface, and that's kind of handling how the JSON objects are being sent over the server. But so we don't need to worry about that. Common filter.cpp really gets down to nitty gritty of the common filter equations. So this was the high level, this is the low level, and then we have its appropriate header file as well. We have main.cpp, which is the main program file that's actually doing all the interfacing between the simulator and, well, main.cpp, which is communicating with our common filter. And then we have some extra like helper packages as well. Measurement package.h is something you won't need to touch, but it kind of helps you with doing just passing on the measurement data to the common filter and for it to process it. And then tools.cpp, which will be doing the calculation for the Jacobian as well as the RMSE. And the code for that is actually, you can just sort of copy it over from the classroom. So we'll look at that later, and that's kind of the last thing we'll do for this walkthrough. So for starters, we can kind of go ahead and maybe check out the main.cpp and kind of see what it's doing. So you won't have to modify this file at all, but it's nice to understand what it's doing. And a lot of kind of the template here is designed so you can interface between the simulator and the C++ code. And you'll probably be getting used to it too, because we kind of used the same layout in main.cpp for all the projects, since they're all involving the simulator. So once you get WebSocket.io working, you'll have that taken care of for all the projects. And then the next time you'll need to install like a kind of maybe a difficult dependency is in the final project of MPC. But we're always kind of looking at ways to alleviate that. So this interface is basically just looking at JSON objects. You don't have to really worry about it. What we'll look at here is a main. So the main thing is that we're initializing our Fusion EKF object here. And we also initialize tools, which was our helper. And then these estimations in ground truth, which will be used later for calculating RMSE. And we pass these objects into this kind of header function here that's looking for messages. We just give it a pointer so it has a reference to these objects, and we can modify it within this loop. So this on message, where we really want to start looking at it is past telemetry right here, and this will loop continuously. So, and with the simulator. So we don't have to worry too much about this. This is seeing if we have a data object, and if we do, we'll process it. So the first thing that we do is we're getting a sensor measurement, and this is actually being delivered from the simulator to the C++ code in this JSON object called sensor measurement. And it's just a string. So we'll grab that string and then we'll process it. The string represents either a LiDAR or a radar measurement. And in this problem with the EKF, we have this object and we want to be able to track it, its position and its velocity, X and Y components. But all we're giving is noisy LiDAR measurements, which are just able to measure a noisy estimation of X and Y, and radar, which is measuring noisy rho, theta, and rho dot. So radar, unlike LiDAR, can directly measure the velocity of the object. And this will help with our accuracy for tracking the velocity X and Y components. So that's what we're given. And our job is to take those noisy measurements and input them into our Kalman filter, and then out comes an estimation for X, Y, and Vx and Vy. And then we plug it into our RMSE function, and we see how accurate that is compared to some ground truth value. And this project is, so unlike just a normal Kalman filter, the extended Kalman filter is doing some sensor fusion. So we have two different types of measurements, LiDAR, which is in Cartesian, and radar, which is in polar. And so they have these different coordinate systems, and with the extended, we're able to take like this non-linearity from the radar component and be able to fuse both of them together to get a nice depiction of what the position and velocity tracking values are. So that's the description of the problem. So we have this sensor measurement, and we're going to break it apart now. First thing we're going to see is what kind of sensor type it is. It's either LiDAR or it's radar. So the letter will depict what it is. And next, if it's LiDAR, the next values will just be the PX and PY noisy values. And then comes a timestamp. So unlike LiDAR, the radar will have three raw measurement components. It has the rho, theta, and rho dot. And the rho dot is kind of like that indirect measurement of the velocity, but only in respect to the sensor's angle and orientation to that object. So it's like a projection of that velocity on that angle. We're just going to store these rho, theta, and rho dot into raw measurements. We have three values, just like we did up above, but with LiDAR, we just had two values, Px and Py. And then we store the timestamp as well for both of them. The next values that come out are the ground truth values. So we have the ground truth X, Y, Vx, and Vy. And this is what we're going to be using later to try to calculate the RMSE and see how accurate our Kalman filter actually is. So we'll be taking each of these values and we'll store them in this kind of ground truth or GT values, and we'll store this in this vector of ground truth. And we'll be using it later for RMSE. And then we actually have all the measurements we need from that first initial string sensor measurement, and we can actually process the measurement. So we built up this measurement package, and now we're going to feed it to Fusion EKF. So one of the first things that we're kind of looking at is we need to go into Fusion EKF.cpp and modify the process measurement so it does this part correctly. And then the next part here is just the estimation. So that's the values that we actually got from our Kalman filter. We got our ground truth values, but how close are these to our actual or to our Kalman filter values? And so we just say, hey, Fusion EKF, I want to take your Kalman filter object and your state vector and just take each of these and then store it in this estimation vector. And then once we have that, we push it into our estimations and then calculate RMSE, which is stored in tools. We'll be grabbing both estimations and ground truth that we calculated up above and see how good our Kalman filter actually is. And then for this project here, the rubric is asking, can you get your RMSE X and Y values below 0.11 and your Vx and Vy values below, I think it's around like 0.52. And so that's the benchmark that we're trying to hit with our RMSE. And last, we just feed in these values to the simulator. So the simulator gave us a measurement, and we're going to give the simulator our estimation of where the object is, its X and its Y, which it'll graph for us. And then we also tell it the RMSE values that we calculated, X, Y, Vx, and Vy. And then so it'll just show up in the simulator. So we can see how the object progresses, how that RMSE values are changing, which is kind of nice. And that's basically it for main.cpp. It'll just send it back to the simulator. The other functions here are you don't have to worry about. It says for the WebSocket server template, it just needs these declared so it can compile. But we're just interested in the common filter main.cpp. So that's all this code right here. So cool. We kind of went through the main.cpp. Let's take a look at maybe the simulator next. So we just checked out this GitHub. And so what if I want to compile it? Well, first thing I'll do is I'll make a new directory called build, and I'll go into that. And this is going to be using our cmake list.txt. So I'm going to be calling cmake and then point to where that cmake list.txt actually is, which is just in the directory right above it. So ... So that'll issue the instructions. And then when I run, I have these make files, and then when I run make, it'll actually go through and compile each of those .cpp program files, C++ program files that I need. So which was main.cpp, which is what we just looked at, tools.cpp, which I kind of described before, which is calculating Jacobian and RMSE, and then Fusion EKF and common filter.cpp, which together make up our extended common filter. So what did that produce for us? Which is this, well, it's this extended KF object right here. And we can call that to try to connect to the server. So if I go ahead and open up the simulator, let's see what happens right now if I just take a blank version of the extended common filter and try to run it. So this is the term 2 simulator right here. So this is a project that we're working with. So EKF and also the same scene works with UKF as well. So we have this object right here, and we're just doing on data set 1, which is what the rubric is grading in accordance to. And if I want to connect with the simulator, I can just run this executable file that I just generated from make. And then it says listening to the port and it's connected. Oh, cool. Well, what happens if I hit start? Well, I actually haven't started programming the common filter at all, so we'll get this segmentation fault core dumped. So that's okay. What we did see was our object still kept moving around, and it created this sort of path. Now let's investigate this path. So here's our object up here, and here's our sensor. And what it generated for us was these noisy measurements. So the red circles are the LiDAR measurements. That's noisy X and Y. Now the blue are radar. And you'll notice what's different about that is it has this angle coming out towards it. Well, this angle is that projected velocity I was talking about earlier. So this angle is always in accordance to the sensor. So you'll see that the angle is pointed this way here. Well, if I come over here, the angle will be in the other direction. So I have all these noisy LiDAR and radar measurements, and what I want to end up getting is graphing these green triangles, which will show the estimated track, and then also get these RMSE values as well. There's also a second data set as well, data set 2. And that's just another extra data set you can play around with. It's not graded, but you can see how well it works with more than one data set there. So cool. That's what the simulator currently looks like with just a fresh checked out version of the code. So let's go ahead and actually start coding it up now at this point. And I will go into kind of this little cheat sheet that I have right here that has some of the functions filled out, but I did it in a way where it's always referencing the quizzes as well. So go into SRC, and then we see all our files here. And let's go ahead and take a look at them. So I'll open up Fusion, EKF. I'll open up Common Filter, and I'll open up maybe just those two for now. So we're kind of going through main.cpp, and the first thing that we saw was that process function. So, and we create that Fusion EKF object as well. So we have a couple of initial values that we have, and most of them are kind of already written for us. Is initialized false, previous timestamp. We have the R laser, R radar, H laser, and HJ matrices here. And we have this R laser, this is a covariance matrix, and R radar covariance matrices here. One thing that we still need to declare is what is this H laser value? So we actually declared it up here, but what does it actually look like? And then I say that it looks like this, and this is from section 10 in lesson 5. Which talks about what the H matrix is actually doing, and that projects your belief about the object's current state. But for LiDAR, we have no idea about directly measuring the velocity. So we're only looking at the PX and PY components, which is why these values over here are 0 and these are 1. And this is the equation that we're actually looking at that does our transition of the state vector with H to get our estimation here. So that's in the classroom. EKF F is our state transition, so that's a 4x4 matrix, and P is also a 4x4 matrix, which is that covariance. We talked about these acceleration noise components, and this is actually talked about in section 13. So let's check that out. Here we kind of say, okay, use noise AX is equal to 3. And then right below that, or we say we're supposed to square it. So right here, I'm just saying use 9 for noise AX and AY. This finishes initializing the Fusion EKF. Now we can move on to that function that we're looking at a little bit before. So process measurement, which is taking that measurement package that we created in main.cpp. So the first thing we're doing is kind of declaring that state vector. We're going to end up overriding these two values here based on just like the initial value that we get. These values you can tweak and play around with. We can't just sort of indirectly get them. And it ends up being pretty important for RMSE. So you can play with these, and that'll pretty much greatly affect your RMSE, because if it's really high, maybe this is really off, and you're accumulating a large RMSE at the very beginning. So let's look at overriding this PX and PY values. If it's, well, let's look at laser first, because that's pretty easy to do. We just set our X 0 and X1 values to the X and Y, which is the measurement package raw measurements, 0 for X and then 1 for Y. And then if we're doing radar, so we're just converting that to X and Y. So we're just going to be doing rho, which is the measurement package raw measurements 0 times cosine, and then theta ends up being measurement package raw measurements 1. So the same thing down here for Y, instead we'll just use sine. So that's how we fill in these first two components here. And this is, yeah, when it hasn't been initialized yet. Next, we're kind of setting up the F matrix. And at first, it's just going to be a diagonal 1 matrix, which is a 4x4. And then we'll kind of fill in some of the parts later, corresponding to what the classroom was telling us. This is pretty important here. Previous timestamp equals the measurement pack timestamp. If you don't do this, then you could end up blowing up your solution getting AN values. So it's important to set this up so when we're using it later after we've done our initialization. And then we'll now say that initialized is true. So next, and then it'll just return. So it'll get out of this. But next time around, when it goes in the process measurement, it'll actually go into our Kalman filter, which is doing a two-step process of prediction and update. So first, let's check out the prediction. And the classroom, again, was talking about this quite a bit. So let's see, we said section 8 of lesson 5 was kind of giving us this state transition matrix. So before, when we were just initializing it, we had this 4x4 1 matrix. You'll notice that this delta T is a component of that. So we need to measure what delta T is, and we actually saved what our old process or our old timestamp was, so we can do that. So the first thing we do is calculate that delta T, and we express that in seconds. And then also then for next time, say now previous timestamp is equal to the measurement pack timestamp, so we can do this procedure next time in a procedural loop. And then we set F just like we were talking about in section 8. And in section 5, we learned about how to set Q. So let's check out, or sorry, section 9 of lesson 5. We get this equation for Q. And then this is actually going to be kind of our prediction step right here. And so basically all we're doing here, and this is in a quiz as well, is setting up Q just exactly based on that equation that's in the classroom. After that, we have Q and F, and we have everything we need to call predict. That's going to look basically like what we have right here for P right there, and then X right here. And let's go ahead and just see what that looks like if we go into commonfilter.cpp, which is what this is calling right here for our ETF object, which is a Kalman filter. And we're doing predict. So here we just say X is equal to F times X, just like in the classroom equation that we saw previously. And P is equal to that exact same equation that we saw too in section 9. So we just basically calculated F and Q, and then once we have those calculated, we can feed it to prediction, and it has everything it needs to figure out what X and P need to be for predict. And that's it for prediction. No matter if you're LiDAR or radar, you're going to be using the same prediction function. And then where it just differs is when you're doing your update. And that's what we're going to be talking about next. So here's the update state. And like I said, it just differs depending on whether it's radar or if it's LiDAR. Let's go over the LiDAR case first, because actually it ends up being exactly the same as just a normal Kalman filter update. So what we do first of all is we set our H, which is just equal to our H laser that we're defining up above right here, which is our 2x4. And then we initialize it right here. So we're using that. We're making sure that we set it, because depending on which measurement, we need to set it each time in this sort of code interface that we're using. And then we set what R is equal to, and that's just that R laser. So that's like the uncertainty in our laser, which ends up being this matrix right here. And once we have those set in our EKF, we just call update. So let's go ahead and check out update. And it turns out that the equations used here are identical to in section 7 of lesson 5, which is just your standard default Kalman filter update, which is right here. Now, I noticed this for the very first time, that it looks like it's doing its measurement update step before the prediction step, but we always do prediction and then update. So I believe that's an error. It's also in this video file here. So it's probably something else you need to take a look at for now, but please just ignore that for the time being. and we'll just focus on the math for doing this update step here. So the code is just provided here, and we basically just set H and we set R before handing it this measurement update. What does H do? Well, it turns out that H times X gives us our Z prediction. It gives us our transition step. And then we look at the difference here, and that's Y. So that's the difference between the LiDAR and the radar, is how this H is accomplishing its task. So that code is identical to what we're actually using right here for doing our update. I think just minus this. Accidentally copied that in. But here is what our new X and P are for the new state. And there's our H times X doing our new transition state. So cool. And then, yeah, you can read more about that in that one section that's talking about how the H of X for radar differs versus the H matrix for LiDAR. And so that's how the update step is working for LiDAR. It's identical to a normal Kalman filter equations. And then what about the radar? Well, it ends up being very similar, actually. So we're setting H and R just like we were last time with a LiDAR, but the H that we're using here, it ends up being the calculated Jacobian, HJ, of the extended Kalman filter's state vector. And then R is just the R radar matrix, which we are defining up above, which is just our uncertainty and how well it's predicting the accuracy of rho, theta, and rho dot. And tools.cpp will actually contain an equation for calculating HJ. And so we're actually going to be referencing how to do that tools.cpp, well, tools.h right here, so we can get that equation for doing the calculate Jacobian. And once we have H and R set, just like we did with radar or LiDAR, we're going to call update EKF. So it's going to be just slightly different, but almost the same. So here's our update, and then go ahead and fix that real quick. Here's our update EKF. And what changes is we need to actually calculate the Z prediction ourselves. And section 14 will give great insight on how to do that. So for radar measurements. And here we talk about H versus H of X. And here's how we do H of X. So X prime is basically just saying that this is after we did our prediction. So the update's happening after prediction, and these X values are basically generated by the prediction step here. So we use those equations to actually calculate what Z predict is. And now, so Y is now Z minus Z predict. Instead of last time, it was Z minus H times X for Z predict. And other than that, it's identical after that. You still, from this line right here, H dot transpose. And you calculate X and P just based on your normal Kalman filter equations there. So that was the end of the update for both LiDAR and radar, and then prediction is the same. Whether it's LiDAR or radar, it's just calculating the DT that you're going to be using for your F and Q. Other than that, you're looking at tools.cpp. Let's see. I'll just and tools.cpp will be handling the calculate RMSE. which main.cpp is calling, and calculate Jacobian, which we will be calling in Fusion EKF later down in the update for radar. And actually, you already calculated, you already created both these functions if you went through the classroom, because they're just at the end here. So here's the Jacobian function here, which is using just kind of that same interface where you're feeding it some X state in here. You're feeding an X state, which happens to be that EKF, EKF.x. And for the RMSE, that's also being done in the classroom right here, where you're given estimations in a ground truth. And that's exactly what main.cpp was gathering as well. And then you can just feed it into calculate RMSE for estimations and ground truth. So yeah, the classroom is a great resource for getting a lot of this code. And it basically just comes down to which section do I need to look at in order to get what code. So I hope by kind of walking through this, it helped to understand where to find each section for how to do this. And that's basically the gist of EKF. This comes down to the prediction and update, and then these extra tools for calculating Jacobians and RMSE. Let's go ahead and maybe take a look at what it looks like in the simulator when it's running, when it's actually filled out. So I'll go into my build, and there's my extended Kalman filter. And I'll go ahead and I'll just open up the simulator again. I'll check out what it looks like for data set 1. And this time when I run it with all the completed functions for prediction and update, I actually get a path of these green triangles. And even though it has all these noisy measurements, it's pretty cool looking at how on track this path seems to be. And we also get our RMSE values. So let's see, in this case, these RMSE values are pretty nice. It actually passed the benchmark for completing the project. So let's maybe talk about for a little bit how to get nice RMSE values, because I kind of mentioned this way back before, but let's just remind ourselves. One of the big things that affects RMSE is that initial X state. And we could peek at what that looks like. So for instance, in the GitHub repository are these kind of data sets. And we could just maybe try out what the VX and VY components are. And so for that, when I was first initializing that one, I was actually using, so I was still setting X and Y based on the initial state of the noisy measurements. But here, I was just trying to experiment. I was looking at what if I set it to actually be VX and VY. And so if that's VX is this 5.2 and VY is 0, and then that's something you end up with. But the thing that you have to be careful of is you have to have it so it's generalizing well too. So if you ran it data set 2 now, maybe you'd see much larger RMSE values, because all of a sudden that initial VX component, where I think it's well, it's positive in data set 1, I think it's negative in data set 2, all of a sudden it's going to accumulate a very large RMSE at the very beginning. So that's something to be careful of, but also something just to kind of understand as well of what's going on right there. So I think that kind of wraps up what I wanted to do for this walkthrough. Without trying not to give it too much away, but also kind of like show where in the classroom to find everything. So I'll go ahead and I think I'll open it for questions now. Okay, cool. So let's see, make sure I didn't miss any questions. Honor asks, are you using Windows 10? And yes, I am using Windows 10. There's some great resources. Well, I'm using the Windows Ubuntu Bash, and there's some great resources that I kind of link to in the classroom in some parts and how to get started with that. And using that is pretty, the UWebsocket.io connection. And then Renard asks, could you mention why we update twice, once for LiDAR and once for laser versus both together? And I think that's just because we're getting those measurements at different times. So we could get them both together and that'd just be the same measurement package. And what makes them be together is that they share the same timestamp. And it would actually be equivalent mathematically to doing them both together. So the answer to that is just there's different times that we're taking in the LiDAR and radar. For the UWebsocket interface, I was using the install ubuntu.sh, but I was running from the latest Ubuntu Bash 16.04. And when I first installed that, I had 14.04 earlier. Updating to 16.04, I thought it was going to be a pain because I was going to lose all my Python and other environments, but actually it turned out to be really easy to get that set up again. So I was actually really glad that I updated it. Yeah, I was using, so Mu27, I was using WebSocket for 14.04, which what made me finally update to 16.04 is when I was looking at the MPC project and it uses some dependencies with IPOP-T. In that case, I couldn't figure out how to get it to work for 14.04, I don't think. So, but yes, you can work with this project from 14.04, but you can't, that script isn't going to work. Like there's one main difference, and that's in how you download or you do sudo apt-get lib1v. You have to use a different package. Something I can try to include is a script that specifically uses 14.04 that helps students out with that. Minora asks if we keep having issues with the simulator. So the thing with that is the other projects are using the simulator all the way up into MPC. So if you can't get the simulator to work, it's going to give you issues later in the future. So, but definitely the Slack is a great resource. I just see people helping each other out there all the time. And like I say, we're working on a better solution too for making it easier to work with these dependencies, whether it be something like a licensed IDE that we give students with CLion, and then we can have direct control over setting up these dependencies like the UWebsocket interface. So that's something that we're constantly working on. But yes, please don't give up on the simulator just because you need UWebsocket.io for all the projects. And then even term 3, like path planning, will be using the UWebsocket. It just because it's such an excellent tool for being able to combine the C++ and then some nice graphical program along with it. I mean, it really makes sense when you start looking like at control projects and things like that. So let's see. And Shamara asked, which files do we need to submit for the project review? I believe the main ones there, I had to double check, but I think the link is just your GitHub, and you can send over your GitHub. But I can tell you that the files that you'll be modifying are the Fusion ETF.cpp. There may be just one or two things you need to modify in Fusion ETF.h, if anything. And then the common filter.cpp. And then once again, with common filter.h, I think almost everything is already filled out there for you. And then tools.cpp. So really, I think it only comes down to three files: Fusion ETF.cpp, common filter.cpp, and the tools.cpp. And then those header files as well, which might have some extra variable declarations. So let's see if there's any more questions. We're at the 47-minute mark right now. So the UKF project will be pretty similar in the sense that you'll be using the same simulator environment for that. The only difference is you'll be doing signal point generation for dealing with the nonlinearity of the common filter. And it ends up being more accurate too, because you'll be using a CBRT coordinate system, well, state vector system. Manji J asked, how you got rho, cos, and rho sine? I don't think these were talked about in lessons. So it kind of comes down to how the radar is actually taking its measurements. And it would be talked about kind of at the very beginning. Let's see, maybe if I can go back to screen sharing and take a look at it. Some of these radar measurements are here, but you could derive it from rho right here for that cosine and sine. So I don't know. I feel like there should be a spot in the classroom that implicitly says the other way around, that px is equal to rho times cosine of phi. But here is another way you could derive it. That's also true with the angle as well. Yes, in Charmis. So the build commands that I was running were from the Ubuntu Bash on Windows, on Windows 10. That's correct. Railguns, yes. In this project, we're assuming that the tracker is stationary. Um, if it's not, you'll be dealing with a tracker that's not stationary in the localization project. And the only difference is you end up having to do a lot of different transformations, show shifting and rotations in order to keep the origin at 0, 0 with angle reference of 0 degrees and things like that. But yeah, just as since this is the first project, it's nice that the car that's sensing this is completely stationary. Ronald asks, why is a Jacobian a bad technique? Yeah, there's this pretty interesting video there kind of at the end of the section saying that the unscented Kalman filter is named because it doesn't use a Jacobian. I think just the Jacobian is a little bit messier than, say, doing the sigma point generation. And it's more kind of work on that part, and it's also not as accurate. And all right, cool. I think I'll wrap it up unless there's any other questions. I hope this helps you go through the extended Kalman filter. Maybe give it just another minute. All right, cool. Well, thanks, guys. Good luck on the project, and I will see you later. Bye.